So right now you should know what a derivative is. You should be able to find the derivative using the formal definition where we looked at the limit as h goes to 0 of that difference quotient. But there's ways to find the derivative which are a lot easier than going through the formal definition. That formal definition, though, should have given you intuitively what's going on to the graph and why we can use what the derivative is. So now I'm going to give you these rules that are going to help us find the derivative in a much easier way than what we've been doing. But I'm going to prove some of these using that formal definition. So let's first look at one of the first rules, which is the derivative of a constant. So if we had some function, let's say f of x is equal to some constant, let's just call it c. So c is equal to a constant. And we probably should say that c is part of our real numbers. So to write that mathematically, I can say c is contained in the set. So contained is that kind of funky e in the set of real numbers. So real numbers, you can denote with a capital R, but the vertical line for the R, there's double. So c is a real number. We'll recall if we were looking at a graph of y equals a constant, that was just a horizontal line. So we would have some horizontal line here going through C. And if we wanted to and find the slope anywhere on a horizontal line, well, the slope anywhere on a horizontal line is always 0. So if f of x is equal to a constant, then the derivative function is equal to 0. So this is the derivative of a constant. And that's our rule. So now, if we ever have a derivative, or we have a function that has just a constant, we know that derivative is going to be 0. But let's prove that. So a lot of mathematics as you get further on is a lot of proving. Why can we use this rule? Technically, I was not a fan of the proving and didn't realize mathematics was like that until I got into upper division. Okay, so looking at this, the proof, we're looking at the limit as h goes to 0, this f of x plus h minus f of x all over h. And we want to show that that's always going to equal 0. Well, if I'm looking at f of x plus h, and my f of x function is equal to c, when I go in there and I plug in x plus h, wherever I see an x, I don't see an x, right? And so it's always just going to be back my constant c. So I have the limit here as h goes to 0 of f of x plus h, which is c, minus f of x. Well, f of x, I would just go in there and replace that with what my equation was. F of x is c, so minus c, all over h. So looking at this, I have now the limit as h goes to 0 of 0 over h. I would have a problem if I took the limit right now because I get that 0 over 0 form. That's an indeterminate. But I also know that that h value is getting closer and closer to 0, infinitesimally close to 0, but never really 0. And I also know that 0 over a number that's not 0 is 0. So I technically could rewrite this limit as h approaches 0. It is the same thing, 0 over h is just 0. And by our limit rule, if we have a limit of a constant, it was just equal to that constant. So the limit as h approaches 0, there's no h in here, or no place to plug in 0 for h. This is just giving me back 0. And so if f of x is equal to c, then f prime of x is equal to 0. And we just showed that using the formal definition of the derivative. Okay, so we're going to prove a great technique to take the derivative, and that is the power rule. So maybe I should write the power rule there. And below is a rule on how to take x plus y raised to some power of n, where n is a real number. Actually, we're going to do it for x or n being a real number, but the proof, we're not going to be able to prove that right now until we get into more mathematics in this course. And so this was where n is a positive integer. So this is a power rule where n is a positive integer. So our exponent be 1, 2, 3, 4, 5, 6, all the way up. And what the power rule says is that if you have f of x equal to x raised to some power n being an integer, then the derivative of that function, f prime of x, this is equal to, we're going to bring down our power in front, n times x, and we're going to subtract 1 from our exponent, n minus 1. So I want to go through and try to prove that that is always going to be the case by looking at the formal definition of a derivative. And while we do that, it's helpful to know this rule, the binomial theorem. You might not have covered it. You might have covered it in your algebra class. But we need to use that rule in order to do this. Okay, so let's prove that. So we're going to let f of x is equal to x to the n. And we want to find the derivative function f prime of x. And we're going to use a formal definition of a derivative. And so we're going to look at the limit as h is approaching 0 of f of x plus h. Well, if I look at f of x plus h, that would be plugging in an x plus h wherever I saw an x in my original function. So that would be x plus h raised to this nth power. And then I would divide minus f of x. Minus my f of x. And my f of x function in here is x raised to the nth. All over h. Notice if I expand this out using this binomial theorem here, and I wrote that all in there, let's do that. So in our case, we would have x to the n plus n times x to the n minus 1. This is h though, not y, because in our case it's x plus h, plus n all times n minus 1 all over 2. This is x to the n minus 2 h squared plus dot 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 plus n x h to the n minus 1 plus h to the nth minus x sub n. So minus this piece now, x sub n. All over h. So if you look at this, our x to the n minus x to the n, those cancel out with each other. Now looking at this, notice that each term has an h involved. We have an h here, Here's a single h, here's an h squared, here's dot, 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 h. All of these have an h in them. So we can technically pull out a single h and then be able to cancel it with what's in the denominator. So if we did that, we pulled out a single h and canceled it with what we have in the denominator, notice what we would have left. Hope you guys are okay with me skipping that step. Well, for the first piece, if I pulled out that h and canceled it within the denominator, I have n times x raised to the n minus 1, plus I would have here this n times n minus 1 all over 2. And then I pulled out an h from the h squared, so I'd have a single h plus dot, 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 plus n times x. If I pull out an h from h to the n minus 1, it's going to have one less h. So this is going to be h to the n minus 2. If I pull out an h from h to the n, there'd be one less there. So this would be h to the n minus 1. I canceled it with the h in the bottom, so we no longer have that denominator. And so if we go in here and we go plug in 0, wherever we see an h, notice the only term that doesn't have the h in there is that first term. So every other term, when we take the limit as x goes to 0, this is going to equal 0. All the pieces in here are going to equal 0. This is going to be 0. We're adding 0. The only thing that we would have left here is n x raised to the n minus 1. So the limit was the derivative function. And so we can say here f prime of x is equal to n times x raised to the n minus 1 power, which is the power rule, which would make life so much easier, right? If you had something raised to some power that got pretty high and you'd have to multiply that out and combine like terms and simplify, it can get kind of tedious. And I'm sure you've seen that it's gotten tedious in the past. But now we have this rule that's going to make our life so much easier. The general power rule. We're just going to write out that power rule one more time. So it says if f of x is equal to x to the nth power, in our case, n could be any real number. We proved it though for n being a positive integer. Once we've gone further in this course, then we'll have enough mathematical tools to prove it for any real number. But for now, we're just gonna go with it. So if we have f of x equals x raised to the n, where n is a real number, so it's contained of our real numbers, then we can say that f prime of x, and remember there was all this different notation. That was not the only way I could write the derivative of f of x. We could rewrite this as d, the derivative of my function f, which is x to the n, dx. This is equal to n times x raised to the n minus 1 power. So in words, the derivative of f of x equals x to the n is found by multiplying the exponent n and decreasing the exponent of x by 1. So it's helpful to be able to rewrite terms in terms so that has exponents. So it is really going to be helpful if you recall the following. So recall radicals could be rewritten to have an exponent. So recall if you had, let's say, the nth root of x raised to the m power, we could rewrite this to have a rational exponent. And so the index, what root you're taking on that radical, goes in the denominator. And what power you're raising it underneath that radical goes in the numerator. So this is equivalent to x raised to the m divided by n power. So if it asked us then, really, if we wanted to take the derivative of a radical, we could rewrite it so that radical is no longer radical, but in exponential form. Other things that are going to be helpful, your rules of exponents are going to be really helpful in these sections. So recalling that, remember, if you have a negative exponent, we can rewrite it positive by bringing it down to the denominator. Remember, anything other than 0 raised to the 0 power is 1. That's also going to be helpful. If we have 0 raised to the 0, that's actually an indeterminate form. We'll talk about that later. But we can't have that, and it doesn't tell us anything. So maybe let's look at an example. So let's say, let's just start easy. F of x is equal to x. And it wants us to find f prime of x. Well, just looking at that, that's a line. We should be able to tell what that slope of that line is, because a slope on a line is always the same. And so you should be able to tell what that slope is, but by using this power rule, we're going to show that. And so using that general power rule, looking at our exponent, well, if our exponent's not shown, it's 1, right? So if you really want to think of it this way, f of x is equal to x raised to the first power. Normally, you just don't write it. And so if we take the derivative, it says bring our power down front. So bringing our 1 down front, x, and subtract 1 from our power. So I'm going to subtract 1 from this exponent. And so this is equal to f prime of x is equal to 1 all times x to the 0 power. As long as x is not 0, we're okay. And if x was 0, that would be different, right? I'll just rewrite that real quick. If x equals 0, f of x equals 0, the derivative of a constant is always 0. Okay, that though, if that was the case, but in this case, this is 1 times x raised to the 0, x is not 0, is 1. So the derivative of f of x equals x is 1, which again, if you think about it, this is in the form y equals mx plus b. In our case, we just have x. My b, my constant, where it's crossing the x-axis is 0. My slope is 1. So we can go further and let k be a constant. So here's another rule. And
I found it for you.
Nice rule, thank you. Not the rule I wanted, Cortana. Let k be a constant, and if g prime of x exists, then the derivative of f of x equals our constant k times our function g of x is the following. Well, we're given that g of x was differentiable. And so this derivative of f of x, f prime of x, this is equal to our constant k times whatever the derivative of g of x was. So the derivative of a constant times a function is the constant times the derivative of the function. Which made sense. We did the same thing, remember, when we had limits, and we could go through and prove this really fast. This one, if we look at the limit as h goes to 0 of f of x plus h, that would be k times g of x plus h minus the derivative of f of x, which is k g of x, all over h. So notice my numerator. I have a k in common in my numerator. I can factor that k out of the numerator. So if I pull that k out of the numerator, notice that we're left with a g of x plus h minus g of x all over h. Bringing down the limit, h goes to 0. Well, rules of the limit said I can take that coefficient in front and pull it out of in front of my limit. So this is the same thing as k times the limit as h goes to 0 of this piece, g of x plus h minus g of x all over h. But by definition, that by definition is g prime of x. So we can rewrite this as k times, well, the limit of this whole piece is g prime of x, which is what we were trying to show. So I'm going to put a box in there showing that I completed and showed my proof. Oh, I was going to give you this example, but I didn't give you that. Basically, if we have the derivative of a sum of terms, then we can take the derivative of each term and then sum them. So let's just use that. And we're going to find the derivative, and I'll write that out tomorrow. Let's find the derivative of y. And so we want to, let's say it gave us different notation. Let's say it said find dy dx. Well, we just looked at techniques to take this derivative without using the limit. And before we do that, sometimes you have to rewrite what your equation is so that we can use that general power rule. And so the square root of x, we can rewrite as x raised to the 1/2 power minus 11 x raised to the 2/3 power. So now it's in the form that we can go ahead and take the derivative. And so dy dx is equal to, so I'm going to keep my coefficient in front times the derivative of x to the 1/2. So I can bring down my power down front, 1/2 x, and subtract 1 from my power. So 1/2 minus 1. So if my exponent is a fraction, I'm usually going to write that 1 as with a common denominator. So I'm going to write that 1 as 2/2, just to make my life easier. Minus, so I have a coefficient in front. I'm going to leave it alone. 11 times the derivative of the other piece. And so we bring our power down front. So times 2/3 x. And now I'm going to subtract 1 from my exponent. So 2/3 minus 1, but in this case, to have a common denominator, I'm going to write that 1 as 3/3. And so let's just go ahead and simplify this. So 2 goes into a negative 100, negative 50 times. So I have a negative 50 here. X raised to the 1/2 minus 2/2. That's a negative 1/2. Minus, nothing simplifies here, but I could, when multiplying fractions, you multiply straight across, so 11 times 2. So this is negative 22 over 3. X raised to the 2/3 minus 3/3. So that would give me a negative 1/3. A lot of times we don't want negative exponents. And so using the rule that if we have a negative exponent, we can bring it down to the denominator to make it positive. And so let's bring this down to the denominator. We'd have a negative 50 in the numerator because that doesn't have the negative exponent piece to it. X raised to the 1/2 minus 22, 3, and then let's bring x to the negative 1/3. Let's bring it down to the denominator to make that exponent positive. Depending on how it's asked, how to write it, this one's a little funky because it has both rational exponents and it has radicals. So to rewrite it, I'm not sure how they would want it, but let's just rewrite it just to get used to it as a radical in both cases. So we have negative 50 all over x to the 1/2. That's the same thing as a square root of x. Minus 22 all over 3 and x to the 1/3. The denominator is what root you're taking. So we're taking the 3rd root of x. And so using the general power rule, coefficient in front of a function that is differentiable is just that coefficient times that derivative. And the sum and difference rule, we could take the derivative of that really easily without having to go use that limit definition of the derivative.